All right, if we could get your attention, we're going to start the spotlights. And we get going. Oh, that goes after that.
Yeah, sounds good. Hi. So I develop a monitor for the prediction module in autonomous vehicle motion stack. So in these two pictures, I show two different kinds of prediction errors. In the top one, the black vehicle is predicted to go straight, but it turns into the green vehicle. In the bottom, the black vehicle turns away. And in the top, this is a task relevant error because it potentially causes a safety critical problem with the green vehicle. So we want our prediction monitor to be task relevant. We also want it to be real time and actually, potentially save the green vehicle from a crash. And we also want to provide a notion of confidence in order to minimize the number of errors for our monitor. And we also want this to be effective without the need to see a bunch of failures, which are potentially expensive to collect. And so our approach is to reason about the effect of prediction errors on the downstream planning cost of our system. So if this sounds interesting, please come by our poster. It's number 417. Thanks.
Hi, everyone. So I'm going to talk about our paper, which is about state estimation for road users for AVs, which is an important problem as the AV interacts with and plans in its environment. This basically results in doing inference of latent state from observations given a state space model. Particle methods are quite effective at this, but they make learning quite difficult, in particular because of the non-differentiability of the resampling step. We present PF-CEPI, which stands for score estimation using Fisher's identity, where we eliminate the need for backpropagating through the resampling step and can hence learn state space models through it in a self-supervised manner. We show experiments with synthetic and real data and show strong performance relative to the baselines. If this sounds interesting, please come find me. And this is quite general and it's not specific to AV problems, so it applies to any space-based model learning. Thank you.
Hello, everyone. This work is about selective object rearrangement on a tabletop. And this task itself is given a goal image. The robot faced with a clutter of everyday objects on the tabletop and is supposed to reposition a subset of the objects in the initial arrangement to the according to the goal image. And there are three main challenges underlying in this task, which is how do you sequence the objects, how to deal with clutter, and how you do selectivity. And to solve this problem, we propose this image-based learned method that involves three phases that includes graph-based object sequencing, feature-based action selection, and visual correspondence-based placement policy. If you found this interesting, please hunt me down at the poster hall just down the stairs, and I'll be there to answer your questions. Thank you.
Hello, everybody. Previous one. All right, there we go. So in this work, we present a sample efficient method for learning dynamical systems. We do this by building upon previous work and using Kubin operator theory, such as extended dynamic mode decomposition or EDMD. And we do this by combining data from the real system together with analytical derivative information from an approximate, although incorrect, analytical model. By combining both of these things together, we achieve a method or a model that performs better than nominal MPC and better than EDMD, while also offering better sample efficiency and generalizability. So we can show that we can do this with only like 10 to 20 trajectories, and we can get something that's good enough to beat all of like nominal MPC. So the key takeaways here are that we should be leveraging what we know and learning what we don't. And critical to this is using derivative information, which is now like very readily available to us. And the last thing is that open loop dynamics prediction error is oftentimes a poor metric, and we should be thinking more carefully about the types of metrics that we use when learning dynamical systems. Thank you.
Unfortunately, this author is not here, so we'll just go to the next one.
I'm Deba Smita, a PhD student at Yale University, and I'm presenting our work on tailoring visual object representation to human requirements. We propose a novel method for a robot to learn visual object representations from a few positive and no negative examples provided by a human. We achieve this using a proposed loss function that incorporates human supervision into a self-supervised contrastive learning method. We evaluate our approach in the recycling domain, where a human selects a few objects belonging to an arbitrary category, thus providing the limited positive examples. A downstream robot passively observes the human and learns a suitable representation of the objects of interest. The robot then uses these learned representations to extract the same kind of objects from a moving stream of recyclables. To learn more, please visit us in the poster lobby. Thank you.
Hi, everyone. I'm here to talk about our work on few-shot preference learning for human-in-the-loop RL. So preferences between behaviors have shown to be an effective way of learning reward functions, but prior works have a few limitations. If you use a linear model, it's very inexpressive and it can't complete complex tasks, but you can learn it in only a handful of queries from a real human. On the other hand, if you use a neural network, you have to use thousands and thousands of queries to train the model, which is completely unrealistic, but they're highly expressive. In this work, we try and get the best of both worlds. And our key insight to doing this is to leverage multitask data in order to pre-train reward models and adapt them later. What we do is we take some prior task experience and we label it with behaviors that we would prefer. Like in this example, there's one drawer that's more closed than the other. We then pre-train a reward model using MAML and adapt it with only a handful of human preferences. In the end, when we compare this to prior methods, we get a 20x improvement in the amount of queries needed to actually learn effective policies. So as you can see, our method in orange vastly outperforms Pebble for a limited feedback budget. So if you're interested in hearing more, come check it out at the poster. Thank you.
Hello, everyone. My name is Hao Zhi. First of all, we are going to present this poster with a real robot demo in the poster right now at the poster lobby. In this project, we show how to train your dexterous hand to rotate a diverse set over 30 different objects using its fingertips. So from a stable grasp, our controller can rotate objects with different mass, different sizes, and different physical properties, as well as objects with holes, objects with low coefficient of frictions, such as the ice ball. None of these objects are seen during training. The controller only sees cylinders in the simulator and transfers to the real world without any fine-tuning or real-world data. So it does not need vision or touch as an input. The only input is the robot drawn positions, and the robot controller will output the delta target positions to control the robot, to control the multi-finger. Please scan the QR code in the screen for our paper code and more videos, and see you at the poster session. Thank you.
Our work on learning Riemannian stable dynamical systems addresses the problem of encoding complex dynamic skills, where the state of the system actually evolves on non-compact Riemannian manifolds. So we initially tested our approach on the two-sphere manifold, which is a compact manifold. And here we can see that we can actually learn stable Riemannian vector fields. We compared this against Euclidean approaches, and we clearly showed that Euclidean approaches actually fail on these kind of settings. We also tested our approach on real robotic tasks, where we actually collected a set of kinetic state demonstrations for grasping tasks or drawing tasks. We collected the motion of the n effector, which actually boils down to a Riemannian manifold. And we showed that using this approach, we can actually guarantee stability in the sense of Lyapunov while being able to overcome different kind of perturbations that you can see in the video right now. So if you're interested, please come by my poster. And also if you're interested of knowing why the Euclidean approaches fail, just step by. Thank you.
Good afternoon, everyone. I'm Karthik Alahari, and I'm here presenting for my student Lina, who couldn't make it for personal reasons. So in this work, we focus on the problem of learning goal condition policies in an offline learning setup. So the requirements in this setup are that we need to learn a policy which allows us to reach any state in the data set. We also need to be able to do this without requiring any additional interaction in the environment, and also with no external objectives. So state-of-the-art approaches for this task tend to use some form of reward engineering or re-engineering, but it is challenging for us to learn in the case of sparse state treating rewards. So we, in contrast, present a self-supervised learning framework to shape the reward function, where we go through a reachability network with learned graph representation, which is the core of our contribution. And this ensures us to have a dense coverage of the state space. So if you're interested, please come by our poster. Thank you.
Hello, everyone. Our work is about 3D reinforcement learning, where the input point counts can be represented in various coordinate frames or coordinate systems. For example, the left figure shows a point count of a dual-arm robot pushing a chair, and the candidate frames include the word frame, the robot base frame, and 2 end effect frames, and the chair frames. We find that different coordinate frames can lead to significantly different sample efficiency, and we thus propose frame miners to adaptively select and fuse multiple candidate frames in a task agnostic manner. Since point count frame mining does not require additional camera views or changing the existing camera placements, so it can serve as a free lunch to improve 3D-R. So please drop by our post session for more details. Thank you.
Yeah, hi. In our paper, we asked the question, do we use the right measure? So in human-robot interaction, we want to adapt robot behavior to user preferences. To that end, we describe user preferences often with a linear reward function, where we have some weights that are user-specific, which then balance the features of a robot trajectory. The goal is then to learn an estimate of that user-specific weight. So our question is, what makes a good estimate? In simulation experiments, when we have access to ground truth user weights, there's 2 principal ways to go about this. The first is to look at a parameter error, where we just compare how similar is the estimated vector compared to the ground truth. Unfortunately, this approach does not give us any information about the reward in the worst case. The second approach is to look at a reward error, where we just compare the collected reward to the optimum. And that, in the worst case, does not translate at all between training and testing. So I'm looking forward to discussing how we can find better evaluation measures at our poster. Thanks.
So hello again. So in this work, we tackle the problem of adapting neural models to changing settings. An example could be changes in the robotic system, as you can see in the video, or changes in the robot's human partner. So to do this adaptation, we propose a simple approach in which the adaptation itself is a byproduct of using dropout masks during training. And as you will see in the video, the adaptation comes to just inferring the appropriate mask to use at runtime. And then we can use this mask to condition the model to this new setting. And here we show the results on this toy example. So to summarize, we propose to infer dropout masks at runtime to allow for model adaptation. And we also have further experiments to show that the masks capture context information. So if you have questions or want to know more, just come and chat with me at level 0, room 41. Thank you.
So hello, everyone. I'm Peng Yun from Hong Kong UST. And today I'm going to present our work, Laplace approximation-based epistemic uncertainty estimation in 3D object detection. So we want to estimate both detection results and the uncertainty in the detection results. So including both classification and each dimension in the regression part. So the contribution of our work is we tailor Laplace approximation for estimating the epistemic uncertainty in 3D object detectors. And the benefit of this method is that we can directly convert a well-trained neural network to a Bayesian neural network to estimate both result and the uncertainty of the result. And here we validate the effectiveness in 3D object detection, and it is not limited in 3D object detection, and you can use this method in, say, manipulation or decision making. So if you are interested in our work, you can come to the room 41. Thank you so much.
Hey, everybody, I'm Kaustubh from Penn, and I'm here today to talk to you about our work on exploring with sticky mittens. And our challenge is to basically tackle long horizons past reward settings, and we like to do so with a little bit of expert intervention. And our motivation for this whole work is the sticky mittens experiment, where kids below the age at which they can grasp are given these sticky mittens with Velcro, and they play with toys with Velcro, and then they just swipe at them and like, whoa, I can grasp. This is so cool. And then once the mittens are taken away, they can still grasp way faster than kids who were not part of this experience. And that's the idea we take away, which is that, knowing the consequence of this option before learning its policy really speeds up learning. And we do so through the option template, which is just the option without the policy. On 3 cool environments, which is like a grid world, fetch and stack manipulation, and Google Research Soccer, football, we have like 2 to 3 orders of improvement. And please come by our poster if you're interested. Thank you.
Hello, everyone. My name is Thomas, and together with my co-authors, I want to present to you today POET, a pose estimation transformer for single image multi-object 6D pose estimation. And our motivation is that we want to take a single RGB image and estimate the pose of every object detected in the image with no additional information such as depth maps or 3D models due to computational limitations or hardware limitations. We achieve state-of-the-art results on the YCBV dataset for RGB-only approaches. And it's a transformer-based architecture that's trainable on top of any existing object detector. We analyze this in depth. And moreover, we show that while 6D pose estimation is interesting for robot manipulation, it's also feasible to use POET in the 6 degree of freedom localization tasks of cameras, which might be interesting for mobile robotics, navigation, and localization tasks. So I'm happy to invite you to my poster or to our poster, and thank you.
Hi, everyone. I'm Tom Silver, and I'm excited to tell you about our work on learning neurosymbolic skills for bi-level planning. We're interested in long horizon decision-making with continuous states and actions. We're really inspired by previous work, especially by George Conadaris, on learning symbols from given skills. But in this project, we're considering kind of the inverse problem, where we start out with symbols and we try to use them to learn skills. The skills that we learn are neurosymbolic. The symbolic components are similar to PDDL operators, and the neural components are like parameterized options. We use these neurosymbolic skills to perform bi-level planning, similar to task and motion planning, where in an outer loop, we use the operators to generate candidate abstract plans. And in an inner loop, we use learned samplers and policies to try to refine those abstract plans into continuous environment actions. Our main contribution is a pipeline for learning these neurosymbolic skills from demonstrations. And please come by our poster to hear about the details. Thanks a lot.
Hi, everyone. Today we present transformers as adaptable task planners. Every person has different preferences, and future robots should be able to adapt to these. So we ask how we can learn jointly the task structure and the preferences from these demonstrations for tasks such as dishwasher loading. We experiment in simulated environment and transfer this policy to a real world Franca arm to load dishes into drawers, and see that this can generalize to unseen preferences with like single user demonstration. Here you can see a prompt showing that 2 plates and a blue bowl were loaded onto the top drawer, and yellow cup and pink bowl were loaded into the bottom drawer. And this was successfully executed with a variable number of objects. For more information, please visit room 40 and find us where we are presenting our poster. Thank you.
Hello, everyone. Today I present to you the Performer MPC. It's a transformer-enabled model predict control frameworks with real-time attention, and that is being designed for real-world navigation problems. So navigation in the real world can be challenging because, for example, if the robot cannot see the humans coming from a blank corner, due to partial observability. Both the human and robot will be frustrated. And what we want is going to be what's showing on the right, where the robots can anticipate such kind of things. So some kind of priors that we can inject to the robots. So how do we do that? So in this way, we use a performer, which is a scalable attention transformer architecture. The inputs are some of the context information, such as occupancy grade, and the outputs would be some cost, which is then fed into a learnable model predictive control frameworks. And if you want to learn more about the details, please come to our poster session. The paper ID is 350. Thank you so much.
Hi, my name is Andrea Saipos, and I'll be telling you about visio-tactile transformers for manipulation. The corresponding author is Yuzu Chen, with contributions from myself, Mark Vandermerva, and Nima Fazeli from the Manipulation and Machine Intelligence Lab at the University of Michigan. The goal of this work is to build compact latent space representations in the joint domain of vision and touch in order to improve RL efficacy for contact-rich robotic manipulation. Fusing vision and touch is non-trivial. Some of the challenges of this task are dimensionality mismatch and complex complementary cues for multimodal feedback. To address these challenges, we propose the visio-tactile transformer, or VTT. VTT utilizes self and cross-attention mechanisms and learnable embeddings to create these compact latent spaces for RL. Now you'll see this attention visualized on simulated and real-world tasks. We can see that when contact is made, the attention shifts to the side of contact in order to help the RL agent complete the task. We found that VTT outperformed 2 baselines in 4 simulated tasks and 1 real-world demonstration. Mark and myself will be at poster 430 in room 040 to take any questions. Thank you.
Last but not least, humans efficiently plan with high-level skills to solve long horizon tasks. Planning on top of the learned skills is how we solve long horizon challenges. Can robots do the same thing? We propose Schemo, skill, and model-based RL. Schemo enables robots to plan abstractly over long time horizons efficiently. Our key idea is to learn a skill dynamics model that predicts the effect of the whole skills. This way, it can skip over the low-level details of skill execution when reasoning over long time horizons. Then it can do faster planning and is less prone to error accumulation. We evaluate Schemo on 4 long horizon sparse reward challenges, and it requires much fewer samples to learn and outperforms all the state-of-the-art model-based and skill-based approaches. We believe there's a lot more potential in learning a skill-based model. So if you're interested in long horizon learning or sample efficiency, please join us in room 40. Thank you.
That's it for the spotlights. Go to the posters. Next thing up is the banquet at 6:30. What's it? Oh, the posters end at 6:10. Oh, well, the schedule isn't finished.